Hello students, today I have come up with the numericals of physics. In my various sessions, I will be taking numericals of each and every chapter, and the questions I will be taking from the Concise Physics Class 10. So today I will be starting with the first chapter. The part A part has numericals in it, and part A consists of about moment of force and equilibrium. With moment of force, we will be seeing some numericals, and there will also be numericals when a meter scale or a half meter scale is in balance. So basically we will be doing the numericals part only. Okay. So the first part, A part, has moment of force. We will be doing the numericals. Before doing any of the numericals, make it a point that you should always have the formulas known. So first we will be taking a look at the formulas, and then we will see the numericals one by one. So the first formula is to find the moment of force. Moment of force can also be called as torque. So I am writing here torque also. So formula will be the same, the two different words for the same thing. So if you have gone through the chapter, you know moment of force is the force multiplied by the perpendicular distance between the point of application of the force and the pivot point. So I have written force and then perpendicular sign I am writing, perpendicular distance, and this perpendicular distance means, again I repeat, it is the distance between the pivot point and the point of application of the force, but that distance should be the perpendicular distance. Okay. Then we go to the second formula, which is couple. So for couple, you know that there should be two forces acting. Okay, they should be in the opposite direction, equal in value, parallel to each other. Okay, then it becomes a couple. The formula is either of the force, because there will be two forces acting. You will have to take either of the two force multiplied with the perpendicular distance between the 2 points. So here I will also be again writing perpendicular distance, but the two perpendicular distance are different. Here the perpendicular distance is the distance between the two forces. Okay. Then we have the next one, where when various forces are acting, the sum of anti-clockwise moment and the sum of clockwise moment will be the same. So that we know it as principle of moment. So we write here sum of anti-clockwise moment equals to sum of clockwise moments. Okay. Now when you are dealing with anti-clockwise and clockwise moment, remember we go with the direction based on how the needles of a clock move. If the direction of motion or rotation is based on the direction with the needle of the clock moves, it is clockwise direction. If it is opposite to that, it is anti-clockwise moment. Remember, we can denote this with plus and negative sign also. Whenever we have anti-clockwise moment, that is taken as positive, and when we have clockwise moment, that is taken as negative. So these are the formulas which we will require. Kindly take a note of all these formulas. We will require them when we solve the sums from the exercise. So we will be beginning with the sums from the exercise. Remember, we will be doing the sums from the Concise Physics ICSE Class 10 book. Okay. So I have the questions here. You will be having the textbook. You can see it from there also. We begin with the first question, which is a very easy and a direct one. The question says the moment of a force of 20 newtons. So this is the force given about a fixed point O is 10 Newton meter. So this is the moment of force given. Calculate the distance of the point O from the line of action of the force. So we have to find the perpendicular distance here. So we should always check that the physical quantities given are in proper SI unit or not. Force is given 20 Newton, it is in SI unit. Moment of force is given as 10 Newton meter, it is in SI unit. So we don't have to do any conversions here. So going with the solutions now. So we have the formula first, moment of force equals to F, that is the force multiplied with the perpendicular distance. So moment of force is given to us as 10 Newton meter. Write the numerical value only while solving. Do not write the unit, it might confuse you sometimes. And then force is given as 20 into the perpendicular distance. So you know this 20 will come and divide here. So I can write here perpendicular distance is 10 by 20. So the 0 will get cancelled. 1 by 2 will give 0.5. We are finding distance, so the unit will be meter, and so this sum is solved. This was a very direct to the formula sums. So let us write the answer. I hope you have understood this. We will go to the next sum. Now let us come to the second numerical. The question goes like this. A nut is opened by a wrench of length 25 centimeter. So if a nut is being opened by a wrench, the length is given 25, means this becomes the perpendicular distance. And take a note, centimeter is not in SI unit, we will have to convert it. If the least force required is 10 Newton, so the force is given, find the moment of force needed to turn the nut. We have to find the moment of force. First of all, this perpendicular distance. This perpendicular distance is given to us as 25 centimeter. So I will write it as 25 by 100, convert it to meter, and I will not calculate here, I will leave it like this only, once only the calculation done during the solving part. So this is done, we have to find moment of force. So let us write the formula. So force multiplied with the perpendicular distance. So force over here is 10 into this one is the perpendicular distance, 1 0 cancelled, 25 by 10 we can put a decimal, 2.5. Moment of force we are calculating, SI unit is Newton meter. So this gives us the answer. Again, a second numerical also is a very direct sum, but pay attention what I have shown you to convert the units whenever required. Now let us come to the third numerical. Now little bit the level will increase. Okay, so let us see the sum. A 50 kg mass is being lifted by using a 1 meter long lever. So this is mass given. We can convert that mass into weight by taking the same value in terms of kgf, because you know that a mass of 1 kgf weight is mass of 1 kg has a weight of 1 kgf. So of this we'll be taking as weight, and then the length is 1 meter, means perpendicular distance is 1 meter. Now if the length of the lever is reduced by 20%, so the length will be reduced. So it is asked how much more or less the force is to be applied. Because the length is reduced, you will quickly tell, okay, more force has to be applied. Okay, but we have to find how much more force required, but the torque has to remain the same. So first of all, we will find what is the torque here. So we write here torque equals to force into perpendicular distance. So force will be taking as 50 kg is the mass, so I am converting it into 50 kgf, it becomes weight, and then perpendicular distance is 1 meter, so I get here 50 kgf meter as the torque. Now this torque is going to remain the same, that will not change, but the length has been reduced, so we will find the new force. But before that, let us find the new perpendicular distance. So 1 meter is the original length. Okay, now it has been reduced, so I will write minus 20%. So 20 by 100 of that 1 meter. So 1 minus 20 by 100 will give me 0.2. So 0.8 meter is the new perpendicular distance. So torque remaining the same, perpendicular distance reduced. So I need to find the new force now. So going by the same formula, so torque, we will write that same value 50 equals to force, new force we have to find. Perpendicular distance is 0.8. So 50 by 0.8 is equals to F. So we get F is equals to 50 by 0.8. Now I can write F is equals to 50 into 10 because I will be removing this decimal. So I get here 2 4s are cancelled, and then 2 5s are, 2 2s are, and this I will cancel 25. So 25 into 5 is 125, okay, by 2, which will give me 62.5 Newton. So you can see that the earlier force was 50, okay. I should change the unit here as kgf. So earlier force was 50 kgf, now it has to be increased, and so it becomes more, and the new force required will be 62.5 kgf. I hope you have understood when two quantities with the change remains the same, the one is changed, how to find the other one by this. So now we come to the fourth numerical. Okay, the question is, the mechanic applies a force of 100 Newton at the end of a spanner to tighten a bolt. So the force is 100 Newton. The length of the spanner is 0.5 meter. This becomes the perpendicular distance. It is asking how much torque is exerted on the bolt. So we need to find the torque first. Then it says that the mechanic increases the force applied by 20%. So this force will increase by 20%. But hold the spanner closer at 0.4 meters. So it is closer at 0.4 meters, not closer by 0.4 meters. Would it result in an increase or decrease of torque? So we can calculate and see whether it will increase or decrease. So first part, let us do it first. The units are given properly. We don't have to convert. So torque is equals to force into perpendicular distance. So force is 100 and perpendicular distance is 0.5. So multiplying will give us 50 Newton meter. So this is the torque, and the first part is done. This is your one of the answer. Now, if the mechanic increases the force applied by 20%, so let us find the new force. So it is increased by 20%, 100 is the already the force, plus 20% increase, okay. So 20 by 100 into 100, this is cancelled, 100 plus 20 will give you 120 Newton is your new force. And the perpendicular distance is 0.4 meters, so we can find the new torque. The same formula, so the force is 120 now, and the perpendicular distance is 0.4 meters. So decimal gets removed because of this 0, 12 fours is 48 Newton meter. So it is asked, would it result in increase or decrease of torque? Earlier it was a torque of 50 Newton meter, now 48 Newton meter. So we will write there is a decrease in torque. So hope you have understood this numerical, how to work it out, okay, and do remember to do the changes in percentage into values and do it. Now let us come to the fifth sums, which has a diagram in it. It is a diagram based numerical. It says the wheel of a diameter is 2 meters. So this is the wheel shown. It has a diameter of 2 meters, okay, with an axle at O. So this is the axle at O, means this is the pivot point. A force F is equals to 2 Newton. This force is acting. F is equal to 2 Newton is applied at B in a direction shown there. So now direction is shown. So we will have to remember whether anti-clockwise or clockwise it will be showing. We will see to that. Calculate the moment of force about the center O. So this, if it is turning about this point, then about this point we have to find the moment of force, and about the point A. If this becomes the turning point, then we have to find based on this also. Okay. So we have to find the moment of force, so we go to write the formula. Always a better habit to write the formula. Okay. So the force is given to us is 2 Newton, which is in SI unit. Perpendicular distance. Now keep in mind what I am telling here. The center O, the pivot point is center O. So the perpendicular distance is this now. Okay, which becomes the radius. So if the diameter is 2 meter, radius you know will be 1 meter. So the perpendicular distance here is 1. So you get it as 2 Newton meter. Now this is the force acting. So as a result, this wheel will rotate like this. So if you are going like this is the direction the needle of the clock will move. So that is your clockwise. So we will write here clockwise. Okay. Or you could also write it as clockwise is in negative sign. So if you write a minus 2 Newton meter, also it is correct. Okay. So about the point O we have got. Now let us find about the point A. So this was the first part. So moment of force. So if I go to write here also about the point A. So the formula is already there. I need not write that formula. The force is the same, not changing, 2 Newton. Now about the point A, so the distance will become this. If this is the distance, this is the diameter, which is 2 meter. So we will be writing here 2. Okay. So that comes to 4 Newton meter. Now if this is the pivot point also, rotation which will take place will be clockwise. So I will write here clockwise. Okay, or we can also write it as minus 4 Newton meter. Both the ways it is correct. So I hope with the diagram numerical you have understood how to take the perpendicular distance. Let us see numerical number 6, another one which is diagram based. Now more and more diagram based sums will be coming. Okay, so follow the question what it says. This is the diagram 1.29 figure. Two forces F1 5 Newton, F2 3 Newton are acting at points A and B respectively of a rod pivoted at the point O. So this is our pivot point. Okay. Such that OA, this length is 2 meter, and OB, this is 4 meter. What we have to calculate first is the moment of force F1 about O. When this force is acting, what is the moment of force we have to find? And in the second one, the moment of force F2 because of this force about the point O. So the pivot point for both of them remains O. And the third one is to find the total moment of the two forces. When both the forces taken into account, what is the total moment? Okay. So first of all, let us go to find the first one, which is calculate the moment of force F1 about O. So moment of force for F1 about O. Equals to the force into perpendicular distance. Okay. So the force here is 5 Newton and the perpendicular distance is 2 meter. So I get it as 10 Newton meter. Now let us look at the direction of it. This force will result in turning it like this. So it means if a turning is like this, it becomes anti-clockwise. So I am not writing anti-clockwise, I am giving the sign there. So I can write it as plus 10 Newton meter also. If you want, you could have written there anti-clockwise also. So now let us come to the second one. So that is moment of force F2 about O. So the same formula will be there. I am not writing that formula, not required. Force F2 is 3 Newton and the perpendicular distance is given as 4 meter. So that is equals to 12. Okay. Now this one will be turning it in this way. So that will become clockwise. So clockwise gets a negative sign, Newton meter. So you could have written minus, I have written, you could have also written clockwise, would be correct. So that is the second one done. Third one is the total moment of the two forces about O. So you know that if we have to find total of anything, we need to add. So here also we'll be adding, but when you're adding, keep in mind to take their signs also. So here we have the first one as plus 10. We have to add, so plus written. And then the other one is minus 12. So you know you can solve it out. Plus minus will become minus. You will get minus 2. Okay, Newton meter. So minus means it will be clockwise. The result will be that when both of them are taken together, it will rotate it in clockwise direction. So final answer, I am writing here this part also, 2 Newton meter clockwise. Hope you have learned here how to apply the moment of forces when various forces are acting and how to find the resultant of it. Okay. Let us come to numerical number 7, which says two forces each of magnitude 10 Newton act vertically upwards and downwards respectively at the points A and B of a uniform rod of length 4 meter. So you have a rod here of 4 meter, one 10 Newton acting upward, another 10 Newton acting downward. Okay. And the pivoted point is point O. Determine the magnitude of the resultant moment of forces about the pivot point O. So here they are asking the resultant moment of forces, but take a look at the question, how the question is here. 10 Newton upward, 10 Newton downward, two forces equal in magnitude, opposite in direction and parallel to each other. So this what I said belongs to what? Belongs to couple. So I can find the resultant of the moment of force here by using the couple formula directly. It will be in a short way, or otherwise I should find it separately for both of them and then find the resultant of it the way I did the previous sum. Okay. So we will apply the couple condition here. So I will write here couple is equals to either force into the perpendicular distance between the two forces. Here we can write only perpendicular distance. So I get here the force is 10 Newton. Remember either of the force, so don't take 10, 10 of both and make it 20. Don't do that mistake. And the perpendicular distance between them is 4 meter. They are in SI unit. So I get it as 40 Newton meter. Now let us take a look at the direction also. This one will try to turn it this way and this one this way. So as a whole, it will be going clockwise. So I can mention here with it clockwise also. So some can be given in a way, but with what is there available to us, we can relate it to make it easier, as I have done here. Instead of using moment of force, I applied couple here. Coming to the next numerical, it's a very important numerical and it tests your concepts whether the point of application of the force and the perpendicular distance which should be taken is clear or not. So follow the question. Figure, this is the figure, shows two forces each of magnitude 10 Newton You can see at both the places 10 Newton. At the points A and B, they are separated by 50 centimeter. Okay, they are acting in opposite direction, that can be noticed. We have to calculate the resultant moment of two forces about the point. Number one is A, means the pivot point is now point A. Then it is second one is point B, then the pivot point is point B. And in the third one, situated exactly, that is at O, situated exactly at the middle of the two forces. So exactly in the middle if it is there, then what is to how to calculate the resultant moment of force. So let us take it one at a time, going with the first one. Okay, so the resultant moment of force, resultant moment of force about the point A, about the point A. So see, there are two forces acting. When we are taking about the point A, that is the force Fa, okay, I will call it as force Fa. So that is, in this, the perpendicular distance, the point and the application of the force is the same. So the perpendicular distance becomes 0. So I'll be writing here Fa into 0 plus, when we are taking FB force, okay, the force FB into, this is the distance, okay, perpendicular distance is this, so that is 50 centimeter, which I will write it as 50 by 100. Okay, so now this is becoming 0, no need to write. Now FB is 10 into 50 by 100, so that will give me zeros cancelled, 5 Newton meter. Now let us take the effect was of force FB, so which is acting downwards, so it will try to rotate like this, means it is clockwise. Okay, first part is done. In the same way we will go to the second part. The resultant moment of force about the point B. So about the point B, when I am taking, because of this force acting at A, the perpendicular distance is 50. So I will write here Fa into 50 by 100, converting it into the SI unit, and the force because of B, the perpendicular distance, the force acting and the point, the pivot point is the same, so it becomes 0. Okay, so now if I put the value, this is given to us 10 into 50 by 100, so that comes to 5 Newton meter. Now look at this force which is here, this is acting in the upward direction, so it will try to turn it about the point B. So this force is acting, it will try to turn it like this, so that will give us clockwise. So this we have got. Now we have to find it about the point O. Okay, so resultant moment of force about the point O. Now see what I can do now. About this point, if I have to find, this is a force 10 Newton upward, this is a force 10 Newton downward, two equal force opposite in direction, parallel to each other. So again I can apply the couple conditions. So I will take either of the force, okay, that is 10, and the distance between either of the force is 50 centimeter. So I am using 50 by 100. So I have applied the couple condition and done instead of doing it separately. Okay, so I will get here as 5 Newton meter. Now let us see the direction. This will be turning it here and this will be turning it here. So ultimately it will come to clockwise. So in all the three conditions, the rotations came as clockwise. I hope you have understood how to take about the perpendicular distance depending upon the force. There are possibilities where the perpendicular distance can be 0 because the point of application of the force and the pivot point is the same. Now let us see the next numerical, number 9, where the diagram is not given. We will be asked to draw the diagram. So follow the question. It says a steering wheel of diameter 0.5 meter is rotated anti-clockwise. So the direction is told it has to be rotated anti-clockwise by applying two forces, each of magnitude 6 Newton. The two forces acting is both 6 Newton. Draw a diagram to show the application of the forces and calculate the moment of force applied. Okay, so let us come with the diagram first. So this is the steering wheel drawn. Okay, we are asked to show the application of the two forces. So I am taking here these 2 points where I apply the forces. We have to draw a proper diagram to show that rotation has to be anti-clockwise. It means the rotation has to go like this. So if I take a look at this point, I should apply the force like this, and here I should apply the force like this. Both the forces are 6 Newton, so 6 Newton written at both the places. Diameter is given as 0.5 meters, so this becomes my 0.5 meter as the diameter. So this is the diagram. You will have marks for diagram. So diagram is properly to be drawn. You cannot miss any of the forces. Okay, and the diameter also. So the diagram part is done. The numerical part is very, very easy. Calculate the moment of force. Again, two forces in equal in magnitude, opposite in direction, parallel to each other. So we can take the couple condition. Okay, so I will write here moment of force equals to F into perpendicular distance. So I have written distance in short now. Okay, so force is 6 into 0.5. So 6 into 0.5 will give you 3. So 3 Newton meter. Because the direction was already mentioned anti-clockwise, you need not write it. But if you write also, nothing is wrong, but it's not compulsory. So this is the answer I get for this numerical. We proceed to the next numerical, number 10. From here onwards, you will start getting the numericals which are based on meter rule, and such type of numericals usually come in the board exams. So how to draw the diagram and the things which I will tell, try to keep them in mind properly and understand them. Question is like this: a uniform meter rule. Meter rule means the length is 1 meter and it is uniform, means mass is equally distributed, is pivoted at its midpoint. So midpoint is the pivot point. A weight of 50 GF is suspended at one end of it. So at any of the one end, it is a 50 GF weight is suspended. Where should a weight of 100 GF be suspended? So we have another weight 100 GF. Where should be kept to keep it the rule horizontal? It means it should be in a balanced condition, equilibrium condition. So first of all, the diagram part is very important here. So let us get a diagram part clear. This is our uniform meter rule. Okay, whenever you get this, please remember to mark these points. Okay, that is the initial point, okay, 0, midpoint 50 and the end point 100. Please remember to do this. Now it is pivoted at its midpoint, so the pivoted point you show it by this way, which is in a way to show the fulcrum. Okay, now 50 GF is suspended at one end, so I am taking this 50 GF to be suspended here, which will try to rotate it in this direction. It is always better also to show the direction in which that force will rotate. Okay, now we are asked where should a 100 GF be suspended. So we know already because of this weight it is getting tilted here. So it has to be suspended somewhere on this side only. So at any distance we can take that. So I am putting it here that 100 GF is suspended, and this part I will be taking as it is suspended at a distance x on the other side of the pivot point. Okay, so I will write here, let 100 GF be suspended at a distance x on the other side of the pivot. Okay, now here comes the use of the principle of moment, that clockwise moment and anti-clockwise moment will be equal. Okay, so I will write here anti-clockwise moment equals to clockwise moment. So anti-clockwise, this one will try to move it anti-clockwise. So the force here is 50 and the distance here is 50 centimeter. We have not changed into SI unit, but we can keep it to the same unit on both the sides and solve. This side the force is 100 GF and the perpendicular distance is x. So I will get here 50 into 50 by 100 is equals to x. So on calculating x, I will get it as 25 centimeter. So it means on the other side of the pivot at a distance of 25 centimeter, it should be kept. So 100 GF should be placed (25 centimeter) on the other side of the pivot. So this is the solution of this one, and I think you have got it how to relate meters rule and draw the diagram. The other numericals coming up will be having diagrams like this only, but there will be more forces acting. We will take one by one and clarify them also. So now you'll be seeing question number 11. The question goes like this. A uniform meter rule balances horizontally on a knife edge placed at the 58 centimeter mark when a weight of 20 GF is suspended from one end. So the balancing point is at 58 centimeter. Question says, first one, draw a diagram of the arrangement, and in the second one we have to find what is the weight of the rule. So let us start with drawing the diagram first. Very important part, how to draw the diagram. So a uniform meter rule is there. So let us have a uniform meter rule, as I told in the previous sum. Very important points to mark are these: starting point 0, the center of gravity point 50 centimeter. 50 centimeter will be the center of gravity. It is a uniform meter rule. Okay, and the end part is at 100 centimeter. Now the question says it is balancing at 58 centimeter. So this part also I should show. This is the balancing part. This is at 58 centimeter. Now it is being balanced by putting a weight of 20 GF from one end. Now see, if this is the center of gravity, if it is being balanced at 58, so the end at which the weight can be put cannot be on this end, because this is already the longer part. So on the shorter arm only, the weight of 20 GF will be there. So I put the weight of 20 GF over here. So this will try to turn it clockwise, and the weight will be taken from the center of gravity, which is 50 GF. We have to find this. So I will write here WGF. This will try to turn it this way. This is the complete diagram. So this diagram is important. It will fetch you 1 mark if it is a 2-mark sums. Okay. Now the solving part. We know that by principle of moment, sum of anti-clockwise moment is equal to clockwise moment. So we will apply that. So according to that, I will write here anti-clockwise moment equals to clockwise moment. Now anti-clockwise, this is turning it anti-clockwise. The force acting is W. So WGF into this distance from 50 to 8 is plus 8 will give you 58. So we write here into 8 equals to, here the weight is 20 GF and the distance from 58 to 100 minus 58 will give you 42. So this is written. Now we can calculate W. 20 into 42 by 8. So I cancel 4 2s and 4 5s. 2 will cancel this 21. So I will get 5 into 21 as 105 GF. So 105 GF is the weight of the rule which we had taken here as WGF. So we get this result. So now let us see question number 12. Okay. The question goes like this. The diagram below, this diagram shows a uniform bar supported at the middle point A. So this is the middle point O. It is supported here. A weight of 40 GF is placed at a distance of 40 centimeter to the left of point O. So from point O toward the left at 40 centimeter, it is 40 GF placed. How can you balance the bar with a weight of 80 GF? So where we should place a bar here, we will have to place it on this side because already on this side a weight is there. Where we should place so that it gets balanced. So we will solve this sum. Let us draw a diagram again for this one to make the things little bit easier. So this is the part here at 0. And at 40 it is 40 GF. Okay, now we have 80 GF to put it on this side. So I am putting it at, think, this place, 80 GF, and I will be taking this distance as X. Okay, so now in this case it is balanced. Okay, and here I should write 40 because it is hanging from the 40 mark. So now my diagram I have just copied. Now we can apply the principle of moment. So I will write here anti-clockwise moment is equal to clockwise moment. So anti-clockwise is this one will be turning it anti-clockwise and this one will be turning it clockwise. So this is 40 GF and this distance is 40. So I write here 40 multiplied with 40, that is the force multiplied with the perpendicular distance. And this side my weight is, the force is 80 and it is at a distance X. So I write here X, so we can write X equals to 40 into 40 by 80. So 42s are 220s are. So I get it as 20 centimeter. So from the point O going towards that side means towards the right hand side. So I will say 80 GF should be placed at a distance of 20 centimeter to the right of O. So this is my answer. So a very simple sum, because the diagram was given, we have to just know how to apply principle of moment and work it out. Now coming to question number 13, let us see the question. The question says in figure 1.33, this is the figure. So the uniform meter rule, this is a uniform meter rule placed on a fulcrum at its midpoint O. So this is the fulcrum part, midpoint O, having a weight of 40 GF at the 10 centimeter mark. This is 40 GF as 10 centimeter mark. And a weight of 20 GF at the 90 centimeter mark. Here is the 20 GF. So it is asking us, first one, is the meter rule in equilibrium? Means is it balanced or not? Okay, so we will come to know by knowing the anti-clockwise moment and clockwise moment. How can the rule be brought in equilibrium? Okay, by using an additional weight of 40 GF. So if it is not balanced, then it is going to turn in which direction? That is also asked. And then how to balance it by using a weight of 40 GF. So again, going by it, we will first draw the diagram of it again. What is given first based on that. So let us draw it. So we have at the 10 centimeter mark 40 GF present here. So this is at the 10 mark. The pivot point is at 50. Okay, that is the point O, and then we have over here a weight acting, that is 20 GF, and it is at the 90 mark. Okay, so this is currently the diagram. So let us see to find both the moments and see whether it is balanced or not. So I go to find the anti-clockwise moment, this one first. So anti-clockwise moment. So weight acting is 40 into the distance. See, this is 10, this is 50. So from 10 to 50, you have 40. So this is 40 centimeter. So 1600 GF centimeter is the anti-clockwise moment. And this one will turn it clockwise. So we look for clockwise moment. So the weight is 20 here into, from 50 to 90, you know 90 minus 50 is 40. So you get here 40. So that is 800 GF centimeter is the clockwise moment. So now we have the value of anti-clockwise and clockwise, and you can see clockwise it is 16, anti-clockwise is 1600 and clockwise is 800. So it means it is not balanced, and because anti-clockwise moment is more, it will tilt anti-clockwise. It means it will come like this down. So first of all, not balanced. Okay, it will tilt anti-clockwise. Okay, it will tilt anti-clockwise. Now comes the second part. We have a weight of 40 GF where we should place it so that it get balanced. Now because anti-clockwise moment is more, so this side is already heavier. So we will have to place it on this side. So I will take this 40 GF to be placed somewhere over here. Now at a distance X. Okay, at a distance X. So we are taking that 40 GF is placed at a distance X. So let 40 GF be placed at distance X to the right of O. So remember, this is our O point. Okay, so right of O. So now we will have clockwise moment and anti-clockwise moment equal, because we are to balance it. It has to be there in equilibrium. So if I take now clockwise moment equals to anti-clockwise moment. So now let us see in the clockwise part. I have written clockwise first. In the clockwise part, already this 800 is there. So I will write this 800 plus there is an additional weight here of 40 GF at a distance x from it. So the total moment becomes here 40 into x equal to, there is no change in anti-clockwise, it is already 1600. So I get it as 1600. So now let us solve it. 40x is equals to 1600 minus 800. 800 goes from here. So x will come as 800 divided by 40, that is equals to 20 centimeter. So this is 40 and x is 20. It means 50 plus 20, 70 centimeter. 40 GF should be placed at 70 centimeter mark. So I will write here 40 GF to be placed at 70 centimeter mark. So this numerical is done. Okay, I hope you have understood. Once it is not balanced, by adding another weight, when it gets balanced, how to find at what place it has to be placed. Now let us come to question number 40, which goes like this. When a boy weighing 20 kgf sits at one end of a 4 meter long seesaw, so the length of the entire seesaw is 4 meter, it gets depressed at this end. So you know, anyone sits at one end, it will go down. How can it be brought to the horizontal position by a man weighing 40 kgf? So there is a man now 40 kgf. Where should you sit on the other end so that they will get balanced each other? Okay, so going with the diagram first. So this is completely 4 meter. So 0 here, middle part will be your 2 meter and the end part will be your 4 meter. Now boy weighing 20 kgf sits at one end, so I am taking him to be sitting at this place, so that is 20 kgf. Okay, this is the balance point, the middle point is the balanced point, and now the man has to sit on the other side. Surely if he sits at the end, complete end will not get balanced because his weight is 40 kgf, he is more heavier. So I am taking it that he is sitting somewhere over here. Okay, and as usual, I will take that distance to be as x. From here till here is x. Okay, so now we apply again that same thing, principle of moments. So I am writing here anti-clockwise. So anti-clockwise moment equal to clockwise moment. The boy sitting over here will be turning it in clockwise, in anti-clockwise. So the weight is 20 kgf multiplied with distance is 2 meter is equal to, the man weight is 40 kgf and he is at a distance x we have taken. So x will come as 20 into 2 is 40 by 40. So that comes as 1 meter. So it means the man has to sit on the other side at a distance of 1 meter from the pivot point. Okay, so man of 40 kgf sits at a distance of 1 meter from the pivot on the other side. This is your answer. So this was a simple sum. Okay, I hope you have understood it. Now let us come to numerical number 15th one. A very simple question this is. A physical balance has its arm length 60 centimeter and 40 centimeter. So we have a physical balance. Here the length of the arms are not the same. One is the longer arm 60 centimeter and the shorter one is 40 centimeter. What weight kept on the pan of the longer arm, means the pan which is there towards the longer arm, at that place what weight should be kept? So that will balance an object of weight 100 GF kept on the other pan. So where the shorter one arm is there, the pan which is there, we are keeping 100 GF. So what weight I should keep in the longer one? Okay. So again, going by the diagram first. I have drawn a fulcrum showing the length to be as different. So in the longer pan which is there, we have to find what will be kept. This is 60 centimeter. So I will be taking there as XGF. Okay. And on the shorter one, the weight which is kept is 100 GF. So this is at a distance length of 40 centimeter. So again here we will have to apply the principle of moments. Okay. So if I write here anti-clockwise moment equals to clockwise moment. So this one will be turning it in the anti-clockwise part. So the weight is X into the length is 60 and that should be equal to the weight 100 into 40. So I get here X equals to 100 into 40 divided by 60. 0 cancel, 2 2s are 2 3s are. So you will get it as 200 by 3. So if you divide 200 with 3, you will be getting it as 66.666. We will write it as 66.67 after rounding it off, and I get it here as 66.67 GF. So the weight on the longer arm, equals to 66.67 GF. This is our answer. Okay, so a very direct sum this was, just applying principle of moment, you get it. Now let us come to the next one, numerical number 16, a long question, but it is a simple one if you do it step by step. Question says the diagram figure 1.34 shows a uniform meter rule weighing 100 GF. So the weight of this rule is 100 GF, that is given, pivoted at its center O. Two weights of 150 GF and 250 GF is hanging from the point A and point B respectively, and then the meter rule says that OA, this length is 40 centimeter, and then OB, this length is 20 centimeter. So calculate the total anti-clockwise moment about O, then the total clockwise moment about O, the difference of anti-clockwise and clockwise moment, which means we have to subtract, and then because it is not balanced, so the distance from O where 100 GF weight should be placed to balance the meter rule. So we are given another 100 GF weight. We have to put it up at a place so that it gets balanced. Okay. I will not be drawing this diagram because we can do it from here only. So starting with finding, first of all, total anti-clockwise moment. Okay. So I go to find so the weight is 150 GF and the distance is 40 centimeter. So I will write here 150 into 40. So 15 fours are 60 and then 2 zeros to be put, 6000 GF centimeter. Because this is asked to find, so you should write the unit. Okay. Now this is our first part. So now to the second part. It is asking us total clockwise moment. So I will write here clockwise moment. Okay. So in clockwise moment, this one will be turning it in clockwise. So 250 is the weight and 20 centimeter is your distance, perpendicular distance. So 250 into 20. So that will give me 5000 GF centimeter. So I know the second part also. Now in the third part, the difference. So we have to minus. Okay. So difference difference in moments. So we will subtract here. So we have 6,000 minus 5,000. So we get it as 1000 GF. Okay. So we have got the difference as 1000 GF and it is anti-clockwise is more. Okay. So it will be turning in anti-clockwise direction. Now the fourth one says the distance from O where a weight of 100 GF should be placed so that it get balanced. Already it is turning anti-clockwise, so I will have to place it at a distance towards the right hand side of this. Okay, so I will take the distance to be as x. So let 100 GF be placed at a distance x to the right of O, to the right of O. So we are placing toward the right of O, so and clockwise moment will change, anti-clockwise will remain same. So writing by the principle of moment, anti-clockwise moment equals to clockwise moment. Anti-clockwise is not changing, so we will write it directly 6,000. Clockwise already it had 5,000. Plus another one has come here at a distance x which is of 100 GF. Okay, so I will write here 100 into x. So I get 6,000 minus 5,000 equals to 100x. So x will be equals to 1000 by 100, which gives us 10. So 10 centimeter comes there. It means it should be placed 10 centimeter to the right of O. So I can write here now 100 GF to be placed 10 centimeter to the right of O. So this sum is done. Okay, I hope you have understood the step by step. Okay, so when you do it, keep a habit of writing and showing all the steps. Now let's see a very small and important sum in question number 17. A uniform meter rule of weight 10 GF is pivoted at its 0 mark. Pivoted point is 0. So because pivoted point is not at the center of gravity, the weight of the rule has to be considered here. What moment of force depresses the rule? As a result, it will not be balanced, it will get depressed because of the weight of the rule. So we have to find what moment of force is doing that. How can it brought horizontal? By applying a least force. So then it can be brought to a balanced condition. So it is asked what least force. If you need the least force, your perpendicular distance should be maximum. Let us show it by a diagram first. So a uniform meter rule. So 0 part is here, 50 in the middle and 100 is here at the end. So the pivot point is at the 0 part, so 0. Weight of the rule, which is 10 GF, will be depressing it by turning it clockwise. And then it is asked also how it can be brought to horizontal by applying a least force. So it is going down. We want to balance it. It should be raised up. Least force required. So it should perpendicular distance should be maximum. So it has to be applied at 100 place. And the least force I am taking it as F. First part tells us to find what moment of force depresses the rule. So I will write here moment of force depresses the rule is equal to, so the weight of the rule will be depressing it, which is 10 GF. and the distance here from 0 to 50 becomes 50. So it becomes 500 GF centimeter. So this is my first answer. This weight 500 GF centimeter is depressing the rule. Now to get the second part. So for the second part, what least force applied? So I told here least force means maximum perpendicular distance, and that force I have taken as F. So this will be turning it in this way, which is anti-clockwise. Okay. So I will take here anti-clockwise moment equals to clockwise moment. Now anti-clockwise, the force acting there is F, so I will be taking that F into, this is the pivot point, this is 100, so it becomes 100, and the clockwise moment was the moment which was depressing the rule, so we already know that as 500. Okay. So F is equals to 500 divided by 100, so that gives us 5 GF. So the least force required over here is 5 GF, which will be balancing this condition. So now let us come to numerical number 18. Okay, question goes like this: a uniform half meter rule. Keep in mind this half meter. This is not a 1 meter rule now. Can be balanced at the 29 centimeter mark. Balancing point is 29 centimeter mark when a mass of 20 gram is hung from its one end. A part says draw a diagram for this arrangement. B part says find the mass of that half meter rule. Mass is asked. Do remember that weight is not asked. In which direction would the balancing point shift? So where the pivot point is there, in which direction you have to shift it? If 20 gram mass is shifted inside from its one end. So where it is there, that 20 gram, it has to be shifted inside, so it will not get balanced then. So you have to change the balancing point where it will be, so it gets balanced. Okay, we will see it part by part, but first of all, the diagram of it. Remember, again, it is a half meter rule. So first is 0, then half of 50 is 25, so at 25 centimeter, and then the end is 50. Balancing is balanced at 29 centimeter mark. So this is my 29. Weight is 20 gram is told at one end. It has to be at this end because before the balancing part the arm is longer. 20 gram told, so weight I will write 20 GF. Okay. Now this we have to find the mass of the rule. Okay. So half meter rule. So I am taking that as m gram. So in weight it becomes m GF. So this will be turning it anti-clockwise. This will be turning it clockwise. So the diagram part, everything is shown here. Okay. So A part, this is my A part solving. Now B part, find the mass of the half meter rule. So we will go by the same way. Okay. Anti-clockwise moment. Now I have written it in short. Okay. Is equal to clockwise moment. Okay. Now anti-clockwise moment, M into 25 to 29 becomes 4 equals to the weight here is 20 into from 29 to 50. Okay, so the length will come as 21. So now M is equals to 20 into 21 by 4. 4 5s is cancelled, so I get here as 105. Because we are finding mass here, so 105 gram is the mass of that rule. So B part is done. Now coming to the C part, understand what is being asked. In which direction would the balancing point shift if 20 gram mass is shifted inside from its one end? Here is the 20 gram. So if you are shifting it here, okay, so if you are shifting here, the length of the arm is decreasing. So if you have to balance, the length of the other side arm also should decrease. it can decrease only if this balancing point is shifted towards 25 centimeter. So it has to be moved towards 25 centimeters. So we will write balancing point needs to be shifted towards 25 centimeter mark. So the moment you disturb 20 gram and take it this side, it will get unbalanced. But if you bring this the balancing point towards 25 centimeter, you can again balance it. I hope this sum has been understood. Okay. Now let us come to question number 19. It has got a lot of things, and this numerical, if you understand it properly, will make all your ideas of this numerical of this chapter clear. Question is like this: a uniform meter rule of mass 100 gram is balanced on a fulcrum at 40 centimeter. This is the point at which it is balanced by suspending an unknown mass m. There is an unknown mass m at 20 centimeter placed, and it gets balanced. We are asked to find the value of that m. Till here this part is very easy. To which side will the rule tilt if the mass m is moved to the 10 centimeter mark? Now if that is moved to 10 centimeter mark, which side it will tilt? We know if we shift the mass, the balance will get disturbed. What is the resultant moment now? When this mass m is taken to 10 centimeter, we have to find the resultant moment there. And then how can it be balanced by another mass of 50 gram? We are provided with another 50 gram. Place it somewhere to balance it. So let us see it part by part to what it is there. But first let us get the diagram of it. Okay. 0, 50 and 100 should always be marked. Now it is being balanced at 40. So this is the place at which it is balanced. Okay. And by mass is suspended of unknown mass m at 20 centimeter. So I am taking here is 20 centimeter mark, and this mass is m. So the weight will be mgf. 100 gram is the weight of mass of the rule. So the weight of the rule 100 gf will be acting from the center of gravity, which in this case is 50 centimeter, because this is a meter rule. Now we have to find the value of m. So the diagram part is done for here. So we go to find the first part. So I will write here anti-clockwise moment, in short ACM, will be equal to clockwise moment. So here it will be m into, from 20 to 40, the length will be 20, and then 100 into, from 40 to 50, the length is 10. So you get it m as 100 into 10 by 20. So 25s are, so mass is 50 gram. So you get the value of m as 50 gram. First part is done. To which side will the rule tilt if the mass m is moved to the 10 centimeter mark? So in the diagram, further part written here at 10, this mass we have got 50 gram. So 50 gf is put here. So which side it will tilt? For that we should know the clockwise moment and the anti-clockwise moment. So I will first go to find anti-clockwise moment. Okay, the anti-clockwise moment, now this is not at 20, this is at 10. So 50 is the mass we had got, so 50 gf is the weight. 10 to 40 is 30, so we get it as 1500 gf centimeter. So we know the anti-clockwise. Now let us find the clockwise moment. So clockwise moment here, this will cause the clockwise moment. So weight is 100 and the distance from 40 to 50 is 10. So that gives us 1000 GF centimeter. So you can look at the values now. Clearly anti-clockwise moment is more. So the weight was shifted, mass M was shifted to that 10 centimeter mark. So it will tilt. It is asked, okay, what is the resultant moment is asked. So we will go to find the resultant moment. So it was asked to which side the rule will tilt. So let us write that answer first. It will tilt anti-clockwise. Okay. Now the third part. What is the resultant moment? So resultant moment, you can see anti-clockwise is 1500 and clockwise is 1000. So we will do 1500 minus 1000. So that will give me 500 GF centimeter, and I am going to write here anti-clockwise. So it will tilt anti-clockwise. So the third part is done. How can it be balanced by another mass of 50 grams? So because it is tilting here, okay, so another mass of 50 gram has to come. We don't know, somewhere it will be here on this side only. So I am taking it here that 50 gram GF is from here. So I will be taking this distance as X I have taken. Okay. So again writing anti-clockwise moment will be equal to clockwise moment. In anti-clockwise moment, this part will not be changing because we have not added the mass towards the left side, which is turning it anti-clockwise. So I will be writing here directly 1500. In the clockwise part, the weight of the rule was causing moment of force, which we had calculated as 1000. So this will be there, plus with that 50 GF coming at a distance X. So this is altogether your clockwise moment. So let us calculate it out. 50X will be 1500 minus 1000. So X will give us 500 by 50, which is equals to 10. Okay. So X we have got as 10. So from 40 to 10 at 50. So it means 50 grams should be placed at the 50 centimeter mark. So I will write here 50 gram to be placed at 50 centimeter mark. So this sum is done. So go through what I have explained here properly, which will help you in understanding how to do numericals of this type. Now let us come to the last numerical of this topic. Okay, the question is like this. In figure 1.35, a uniform bar of length M. So M means that is n meter. So this is your bar, okay, is supported at its end. So the support is at the end, okay, and loaded by a weight W kgf at its middle. Exactly in the middle, a weight W is kept. So these two are the part where it is rested, okay, and this weight is pulling it downward. Find the reactions R1 and R2 at the end. So these two are the reactions because it is placed on a support. So this weight is pulling it down. So this part will be applying a normal reaction force upward. We have to find R1 and R2 here. Okay. So let us see how we will work it out. Okay. The entire length is L. Okay. So it means from here till here, the length becomes L by 2. Same way the length here, this side is also L by 2. But first of all, here we will relate the resultant of the forces which are acting here. Weight W is acting in the downward direction and the two reactions are in the upward direction. they are in balanced condition. So the total force in the downward direction should be equal to the total forces acting in the upward direction. So that will help us in getting this relationship. W will be equal to R1 plus R2. So I have named it as equation 1. Then we will apply the principle of moment here. Okay, the weight which is there is trying to turn it. Okay, and the distance is L by 2. Okay, so this R1 will be trying to turn it up this side, so it will be clockwise, and this one will try to turn it anti-clockwise. So we go to write anti-clockwise moment is equal to clockwise moment. So anti-clockwise moment, because this one will try to turn it this way, so R2 into the length, the perpendicular length from here till here, which is L by 2, is equal to the clockwise moment R1 into L by 2. Now both the side you can see L by 2 is there, it will get cancelled. So you get R2 is equals to R1 as equation 2. I can put this R2 value in equation 1. So I will write here using equation 1. So W is equals to R1 is copied as it is. In place of R2, I am putting R1. So I get 2R1 is equals to W. So R1 will be equals to W by 2. So the reaction which is here R1, I get the value as W by 2. So whatever will be the weight, here no weight is given. If the weight was known, we would have got half of that weight as the reaction R1. And because R1 and R2 are equal, so that will also be the same value. So this sum is done by applying the equilibrium condition for the resultant forces as well as the principle of moments. So with this, we come to the end of the numericals of force part A. I hope all the numericals you have understood. You are able to now in a condition to work out the numericals, select numericals from other textbooks and try to work them out. If you have liked the video, please do remember to subscribe my channel, because I will be coming up with the numericals of the other chapters also, and also to like this video. Thank you.